Hello everyone, my name is Bowei Li, a second-year PhD student in TWI laser section. Today my presentation topic is laser riveting, an innovative technique for dissimilar composite to metal joining. As we know, composite is a high-promising material, which has high strength but with low weight property. So it is widely used in the aerospace and automotive sectors. For example, this 787 airplane, we can see that the half of its body's material is composite. Rest are different kinds of metal, like aluminum, steel, and titanium. So here is a problem. Because of their quite different material properties and structures, how could we join them together properly? Currently, there are two main methods for dissimilar composite to metal joining: mechanical fasten and adhesive bonding. Both of them are mature technologies, have certain benefits but still exist few shortcomings in some specific conditions. For mechanical fasten, the advantage is its very short processing time. It can be completed in only few seconds for a single joint. But we can see it in the picture. The drawback is obvious. It will draw a hole throughout the metal substrate, which is unexpected in load-bearing structures. As for the adhesive bonding, the merit is that it can avoid the damage on the substrate, but because of adhesive property, it also has some requirements of long-time surface pretreatment and several environmental limitations like temperature and humidity. So this project, laser riveting, aims to develop an innovative joining technique with high efficiency and keep an intact metal substrate. Meantime, its joint is unaffected by environmental factors. So how could I achieve it? Here is the concept of the project. The whole procedure is divided in 3 steps. First, drill holes in the composite sheet and put it on the metal substrate. Then feed the wire and deliver the laser to melt it. Process the laser metal wire deposition in the hole. After it solidified, it will form a rivet to interlock the metal and the composite sheets. Therefore, according to this concept, there are 2 key points. First is the laser wire deposition on the metal substrate, and another is the interactions between the melt wire and the interface of hole in the composite sheet. Because I am a second-year student, before working with composite directly, I want to investigate the laser wire deposition processing systematically. So the last year, my work was only focused on the study of laser wire deposition on the metal substrate. In this presentation, I will introduce my work results step by step, from feasibility study to parameter improvements and further experiment trials. Then let's move to the experimental part. This figure shows the laser metal wire deposition processing system in the lab. Here, at the bottom is a clamping device. Above the substrate is a wire feeder and shielding pipe, which protects material from oxidation during the processing. At the top is a laser processing head with its CNC control unit. This motion unit is a 3-axis system, so technically, it can glide any pattern or route designed by program. For material selection, the metal substrate I used in the feasibility study is Thai alloy, and stainless steel is used for parameter studies. And the feeder wires are same type Thai alloy and mild steel. Both of their diameters are 0.8 mm. Currently, there are numerous researches about the wire deposition on a straight line path. but still has very limited reference about the circular path and cylinder building. Since there are complex phase change and wettability problems involved, I need to make sure that the melt wire can be collected in a small circular path and successfully build up a cylinder shape like a single rivet. So at the beginning of this project, the first experiment I need to conduct is a feasibility study of wire cylinder deposition on the metal substrate. After some initial trials, in the left hand, a 3-arc path strategy was developed. It is a similar circle route with 3 deposition paths. Because of the wire feeding angle issue, in the DA arc, wire will stuck in the deposition. So in this strategy, the wire will retract at D point and only laser scanning left in the final arc to let the melting material flow to fill this gap area. Then based on the 3 arcs experimental results, after the improvements on the wire feed and retract points, in order to fix the angle issue, in the right hand, a full circle path strategy was developed, which has a full circular deposition path to feed the wire and an extra wash path to let the laser scan the deposition so that make it flatter. Following slides will show the results of single and multiple layer depositions applied by these 2 strategies, both in geometrical and macrostructural aspects. This video played in the left explains the deposition processing of 3-arc strategy. As we mentioned before, wire is deposited in former 3 arcs, and then only laser scanning is processed in final arc. After the cooling time, second layer will repeat the same action. Let's see the figure 4 for the single colliding pictures in the microstructure map at the right side. We can clearly see that the alpha grains transfer to the beta grains gradually from base substrate to added material, which shows the agreement with other relevant researches. But in another point, obviously, because of lack of material input in the final arc path, it leads to the uneven material distribution and an inside cavity formation. The similar problems also appear in the multiple layers deposition in the figure 5. Although it can successfully build up the cylinder rivet, but the cavity and the deposition angle issues are still exist. So after the adjustments in the full circle strategy, the material input will cover all the paths, and an extra wash path is also added to fix the current issues. The left video shows the full circle strategy's deposition. Differ to the previous one, in this path strategy, wire feeding will cover the whole circle, and with one more laser scanning circle to make the deposition smoother and flatter. Consequently, we can see the result in the figure 6 and 7. The cavity and incline issues are significantly improved, both in single and multiple layers deposition. And look at the interface between the added material and the substrate. They have joined quite well in the microstructure maps. Therefore, although both of 3-arc and 4-circle strategies can successfully build up the cylinder deposition, after the results analysis and comparison, we can easily conclude that the deposition applied by 4-circle path strategy can achieve a better result, both in the geometrical and macrostructural aspects. Moreover, it has already satisfied the basic requirements of this feasibility study, so it will be used as control group in the next parameter improvements study. After the feasibility study, several parameter influences of steel cylinder building have been investigated, such as power, travel speed, wear fitting speed, and height adjustment. But as we mentioned in previous, the time cost is another vital factor to an industrial application. And for the full-circle strategy, to build up an 8-layer cylinder, it will cost almost 2 minutes for the whole processing. So processing time reduction is the main goal in this parameter improvement study, and the full-circle strategy will use as the normal deposition method. Based on it, through adjusting the processing parameters, following 4 deposition method was designed. In the high-speed deposition 1 and 2, I increased the travel speeds of deposition and wash pass. Meantime, the cooling time of each layer is also reduced. And after the trials, to get a faster processing procedure, the wash pass and cooling time were removed. So in the continuous spiral method, the wire will keep fading from beginning to the end, and the deposition route is like a spiral from base substrate to the cylinder top. Then I increased the deposition speed to complete the final design of high-speed spiral deposition. The next slide is a video to show the processing difference between the initial normal deposition and the final high-speed spiral deposition. In this video, the left is initial normal deposition, and the right hand is the final spiral deposition. We can see that after increased the travel speed and removed the cooling time, the whole processing time is dramatically decreased. For high-speed continuous spiral deposition, it only needs 14 seconds to build up a 6-layer deposition, but for the normal method, it still needs 94 seconds. And this slide shows that the results comparison of different cylinder deposition methods. At left is the processing time chart. We can see initial from normal to high speed, then final to the continuous spiral deposition method. The time cost is gradually and sharply decreased. All the multiple depositions which applied HS continuous spiral method are saved around 85% time compared to the normal method. Right chart is the height results of these cylinders, but there is not too much difference. But because longer deposition time and lower energy input, the normal continuous spiral has the largest value among them. These are the further experiment trials of tie-alloy spiral deposition and dissimilar joining between aluminum and steel. They still need more evaluations and systematically investigations. Besides the experimental part, the numerical simulations are carried out as well. There are 2 modelings presented in this slide. Left hand is a straight line model and the right is a spiral deposition. Their mass input realized by the inactive elements method in the opcos, and the energy input is controlled by the user-defined subroutine. So it can precisely describe what happened in the experiment processing. Graphs below are the temperature data comparison. The thermocouple's position at the bottom of substrate. The blue line is experimental result and the red line is the numerical modeling data. They have shown a high agreement in the thermal history, so it means that this modeling has certain reliability in the temperature field simulation and prediction. Based on it, in the future work, a residual stress modeling will be developed to analyze the parameter influence on it. So above are all the work I have done in my first year. They all focused on the laser metal wire cylinder deposition, which has a feasibility study to deposit a proper cylinder. Then the parameter improvements to significantly reduce the processing time. What's more, a new thermal analysis numerical modeling has been developed. to calibrate the experimental result. So for the future work, my focus point will move to the dissimilar joining. The first thing is apply the current cylinder deposition method to join the metal to the composite. Then after I get these joints, they will be evaluated by various analyses and develop a deeper understanding of the process. Moreover, composite will added in current numerical model to assist the experiment to predict it under different conditions. Thank you for your listening, and any question is welcome.